and land cover change, the scale of that sink becomes much smaller. In other words, we are being quite effective as a species at removing the ability of the land surface to act effectively as a sink. However, this is highly regionalized. There are places where CO2 remains very active, is being sunk very actively, in other places it's not. And this is from the IPCC report. This isn't all that easy to see, and I'm really only interested in the first two bars on all of this. There's two stories here. The first bar is the terrestrial flux in the 1990s, and the second bar is the terrestrial flux in the 2000s. So the two stories I need you to get from this is, first of all, there's strong regional variability in the magnitude of the sinks. So a lot more CO2 is going into the land here than, for instance, here. Now, this is an awful figure. I don't know who drew it for the IPCC, but the y-axis is in petagrams of carbon, or gigatons of carbon. A gigaton of carbon is 1 billion tons. So there's quite a big difference between 0.2 and 0.5. We're talking about an awful lot of carbon. So it's a bit difficult to see the subtleties of this on this particular figure, but you should be able to see, for instance, that bar there is shorter than that bar there, i.e. there's regional differences between where the CO2 is going. And if you've got sharp eyes, you will see that that bar there is longer than that bar there, implying a reduction in the terrestrial sink. That is the opposite of, for instance, in some of the areas of the tropics where it has increased. Short story, the place that the carbon is going into the land surface is highly regionalized and quite variable over time. If you want to know much more about that, there's a chapter on biogeochemical cycling in the latest IPCC report. The basic results from our climate models are quite different from that. So climate models tend to simulate the land surface becoming an increasing sink. This is quite important. If you do a climate projection through to the end of the 21st century, and your land surface scheme energetically sucks up carbon, there's less CO2 in the atmosphere. And that means the effective CO2 in the atmosphere is lower, so radiative forcing is lower, so the climate change signal is lower. If, in contrast, your land surface can't take up billion tons of CO2, you end up with a lot more CO2 in the atmosphere, a lot more radiative forcing, and a much stronger sensitivity to the increased CO2 in terms of temperature, the climate sensitivity. So this is quite important because it's not clear how much CO2 the land will be able to take up in a sustained way through to the end of the 21st century. In addition to that, there are things called nutrients. If you go into your cupboard, if you have a garden, and grab some fertilizer off the shelf, those little packets of soluble fertilizer, and look at what's in them, there's nutrients for your plant to make your plants grow nicely. And most of those nutrients are things like nitrogen and phosphorus. And nitrogen and phosphorus also act as significant limitations on how plants will respond to increased CO2 in the atmosphere. Climate models in CMIP 5, so the last IPCC report, virtually none of them included nutrients in terms of their standard, classic, how will climate change by the end of the century simulations. Some included one of those nutrients, nitrogen. And if you include nitrogen limitation, you get a much, much smaller impact, or a much smaller capability of the land surface to take up the atmospheric CO2 pumped into the atmosphere. That's what that slide there shows. This is a simulation with a climate model, actually CSIRO Mark 3L, for those of you interested, showing the pattern of reduced carbon uptake in gigatons as a consequence of adding nitrogen limitation into the land surface. Note, it's almost always negative, i.e. a reduced carbon sink, and note it's highly regionalized. So we see through the boreal forests of the northern hemisphere a substantial reduction in the amount of CO2 that those vegetation could take up as a consequence of nitrogen limitation. Also note a really strong positive signal, one of the places that does seem to benefit, over China. The next stage was to add a second nutrient in, which was phosphorus. Note that broadly, relative to nitrogen, phosphorus has a much smaller effect, except it strongly reduces the amount of CO2 taken up over China. Yeah?
Does that include nitrogen fixing plants? With the
It includes a model called CASA-CNP, and the detail of how CASA-CNP parameterizes nitrogen limitation is something I do not recall. Anyone, do you know? Does? Yeah, it does, yes. Confidently does?
Fixation's not done well. There's normally assumptions about how it varies with, as a function of ET, for example, is a common assumptions made. It's a huge uncertainty in models, is nitrogen fixation in the future.
Yeah, and so is the impact of phosphorus limitation in the future. All I'm trying to get across is not the detail, but the fact that most CMIP5 model simulations don't include nutrient limitation. Therefore, they're probably overly able to suck up CO2. This comes back to something called allowable emissions.
Has anyone looked at the interaction between those two?
Yes, that was in the paper. The paper by Zhang et al., which I can point out. I can provide you now. This comes back to something called allowable emissions. You will all know that the limit, apparently, to avoiding 2 degrees is 1,000 billion tons of CO2 emitted post-industrial activity. We'll argue the toss over the 1,000 billion tons at your leisure, but let's assume it's 1,000 billion tons. That's on the assumption of certain resilience of things like terrestrial and ocean carbon uptake. If we have grossly overestimated the capability of the land surface to suck up CO2, and the land surface, because of these sorts of things, will not be able to suck up CO2 as effectively, then the amount of CO2 we can emit and stay under 2 degrees becomes a much smaller number. So this stuff actually matters. It matters because it feeds into assumptions on how much CO2 can be emitted by humans and still avoid a 2-degree global warming. So nutrients are not totally esoteric. They actually feed right into the heart of assumptions written into things like the Paris Agreement. Going to move away from nutrients, which I am no expert on, into land cover change, which we can argue about later. I like land cover change.
Can you just be explicit?
I thought you were on leave. Sorry.
Can you just quickly outline the exact process that land surfaces act as a sink? Like, the trees take up the carbon and then it gets put into the soil. How?
Yeah, I touched on that in the previous lecture, but clearly enough.
Sorry.
Sorry. Okay. So yes, vegetation sucks up CO2. It fixes that in the form of carbon, and it allocates the carbon either into roots or into stems or into more leaves or whatever, and it stores that carbon in the land. Ultimately, some of that gets recycled down into longer-lived carbon in the soil, and some of that carbon can exist in the soil for very long periods of time, commonly known as coal, ultimately. So the land is very effective at taking CO2 out of the atmosphere and storing it. How effectively it does that depends on many, many things. Matt works in urban environments where carbon isn't the most important feature of the landscape. Land cover change. This is not a natural landscape. This is wheat. Wheat doesn't behave like a natural landscape because it has been selected over many thousands of years to not behave like a natural type of vegetation, because it takes in as much CO2 it can and grows as big a thing that you then grind into making flour. So it's not natural. This is also not a lateral landscape. This is an Asian city, and that does not interact with the atmosphere in the same way as a tropical forest would. This is a natural kind of vegetation. This is my favourite tree. It's a eucalypt. And eucalypts behave very differently, we think, to many northern hemisphere vegetation types. If you're interested in land cover change, one of the reasons you're interested in it is because if you clear a landscape, and this is a landscape that's been denuded of vegetation by either overgrazing or clearing or drought or some combination of all of those, it behaves quite differently from the natural landscapes that would have previously been living there. Here's another example of land cover change. It's fairly obvious. This is in South America, large-scale clear-cut felling. The left-hand side of that interacts with the atmosphere very differently from the right-hand side. And similarly, crops that are struggling because they're limited by water interact with the atmosphere very differently from a well-sustained, freely growing crop. This is my favourite kind of land cover change, or second favourite perhaps. This is a road. This is a road after a heat wave. I think it's a really cool photograph. Urban landscapes do not behave normally. They melt. On the whole, natural landscapes don't melt. This is a famous example from Tom Lyons in Murdoch University in Western Australia. It's the iconic figure. This is a photograph of Western Australia, and running along there where you can see the dark natural vegetation from the light agricultural landscapes is what's called the bunny fence. I won't ask you why it's called the bunny fence, because it's fairly obvious. It's a fence to keep out bunnies. On the right-hand side, the bunnies frolic happily eating stuff. On the left-hand side, the bunnies don't get in. And you can see, to a degree, the consequences of that. Also, note the clouds on the left-hand side of the image and relatively clear sky on the right-hand side. Much more evaporation, much cooler over here, much less evaporation, much drier over here. Land cover change is a big deal. Those of you around in 1500 would have recognized this as a kind of a pattern of vegetation. And I'm just going to leaf you through centuries to show you two things. First of all, at the large scale, most of the regions of intense land cover change were already changed in 1500. There is a really cool book called Deforesting the Earth by a guy called Williams. I would lend some of you a copy of it if you're very well behaved. It's quite thick and it's written by a historian, and it's amazing. It documents the history of land cover change and deforestation right the way back to ancient times, and talks about things like the deforestation of Britain, not to build Henry VIII's ships, but to generate the charcoal necessary primarily for the making of weapons. You needed the charcoal to get the steel hot enough. Anyway, you could go read the book. It's also a very interesting book because it only gets really passionate in one sentence, which is about the brutality of the land clearance in Western Australia. Because the Western Australians were amazingly effective at clear felling the whole region. Anyway, this is land clearance in 1500. And I'm going to skip through, and I want you to see that the area of land cover change doesn't change that much. But this axis is the intensity of land clearance from very low, 10% of the area, up to very high. So by 1600, it hasn't changed that much. There's been a little bit of an increase in the area, but if you look over Europe, France had happily chopped most of its trees down, and that merely intensified a little bit and spread a little bit north into places like the Netherlands and Germany. and my geography is going to rapidly degenerate from this point on. 1700, not much change, really. A little bit into South America, a little bit of intensification over northern China. 1800, much the same. 1900, big deal. The consequences of much more urban and industrial development saw a rapid change from 1800 to 1900. Look over North America. You'll also note a really interesting thing over Australia. If you go back to 1800, Australia had not been touched. Remember, 1788 was when Westerners arrived, had actually been substantially modified by Aboriginal burning prior to that. But between 1800 and 1900, apparently the whole continent got changed. This draws us to how these data were constructed, which was based primarily on data around trade. And Australia is lumped in with Southeast Asia in the way that this data was created. There was very substantial timber trade from Asia into Europe in this period, and the whole region gets signalled as having undergone land cover change in that time. So, in other words, don't trust reconstructed data too strongly. 2000, it's been a bit of a change. So we go from 1900 to 2000. Again, the area change is not that dramatic, but the intensity of the change is profound. And so we're now up around 50 to 60% of all land area having been substantially modified by human activity. Yeah.
What have they changed in the deserts of Australia?
So, sorry, I was trying to make the point that when these reconstructions were done, that whole region there was lumped into one region, and what they did was worked out how much timber was exported and how much land cover change must have happened over the whole region, okay? And then spread that change over that whole region because the data aren't that rich. So there has been land cover change over lots of Australia, but I don't think really to that extent. In fact, I'm sure not to that extent. So that's 2000. Lots of land cover change. Hence, it would be a good idea if our climate models incorporated it. Most of our land surface schemes don't really care all that much about non-native vegetation. Okay? We do kind of worry a little bit about crops, and urban areas are parameterized excruciatingly simply. But this major transformation of natural landscapes to human-modified landscapes in the real world is very significant, but in how climate models parameterize those processes is handled very simply. So why does all that matter? Well, first of all, deforestation affects the amount of net radiation. Deforestation affects the reflectivity of the surface. Forests are dark. Tropical forests might be as dark as 0.1. 90% of the radiation incident on them is absorbed. Only 10% is reflected. Whereas grasslands might have reflectivities up to 0.3. 30% of the incoming solar radiation being reflected. So deforestation affects the amount of net radiation, the actual amount of energy available to drive the system. And that means it must also affect the fluxes that we discussed last hour and how those fluxes are partitioned between the sensible heat and the latent heat. Deforestation almost always reduces the effectiveness of the land at transferring moisture into the atmosphere, and then therefore tends to reduce the latent heat flux, and consequently must increase the sensible heat flux, because the soil heat flux is a fairly small term. So, deforestation profoundly changes the balance of the turbulent energy fluxes that either moisten or heat the boundary layer. So, deforestation reduces evaporation. It's not hard to conceptualize. If you look at this slide, you've got to, I think, imagine that the evaporative flux from this is going to be lower than this. And if the evaporative flux here is lower, it's going to have consequences differently from this. But in broad terms, albedos, forests are much darker, they're much rougher, they mask snow effectively. If you walk across a landscape where there's decent amounts of snow, the snow completely covers the grasses and perhaps shrubs, but the trees stick up through the snow and remain dark relative to the snow-covered surface. Land cover change dramatically affects the ability of vegetation to access water, because trees tend to be able to put roots down much deeper and access water that's much deeper than the replacement vegetation and the grasses. They have different characteristics in terms of stomatal conductance and the ability to transpire water. And I've forgotten the math, or I would show it you, there's papers by a guy called Bob Dickinson that shows that there is more leaf in contact with the atmosphere than there is surface area of the planet. So if you imagine the whole surface area of the planet as a sphere, there's more leaves in contact with the atmosphere than there is surface area of the planet. Because if you stand under a tree and look up, there's 3 or 4 or 5 times the surface area of leaf above your head than there is surface area below the tree. It's called leaf area index. And leaves are much, much more in contact with the atmosphere than a bare soil surface. And vegetation also does a pretty good job at intercepting water. That's important, right? Because if water hits the soil surface and infiltrates, it might get lost down to a stream and removed down to the ocean, or it might stay in the soil for days or weeks or months. Whereas a leaf tends to get dry within minutes to hours. And that means that water is recycled back up into the atmosphere for future rainfall within minutes to hours, whereas if it gets to the soil, it might stay there for months. And you start to change the timescales at which the surface is interacting with the atmosphere. So, land cover change tends to change the albedo and change the net radiation, which leads to changes in temperature. It also reduces the evaporation, which increases the sensible heat, which tends to warm. And the reduction in the latent heat tends to reduce clouds, which tends to increase the amount of sunlight coming through, which also tends to increase temperature. There's multiple interacting processes. That should have been a plus for those of you who are paying attention, not a minus. Tends to be that land cover change increases the reflectivity and reduces net radiation. I've got my sign convention wrong. So here's what happens in a climate model. This comes from a project called Lucid, where a number of different climate models were run with a common land surface perturbation, or land cover change perturbation, and we looked to see what the impact would be. So this is from one model. It happens to be from the IPSL model, which uses a land surface scheme called Orchidae, which is a really cool acronym if you know your plants. Oops. So the first thing to say is that you will see colours on the latent heat or evaporation that tend to be reds and oranges, which mean a reduction. Reduction in the latent heat flux tends to lead to an increase in temperature over the same areas, and maybe changes in rainfall. And there's a lot of argument over the ability of a change in the land cover to affect rainfall. This is a globally averaged picture in the same analysis. The bars that are open bars for both the latent, the temperature, and the rainfall are the changes that occur where you've chopped down the vegetation, where you've actually changed the land. And the black bars are changes that are remote from the land cover change. And that little dashed line in the middle there are the changes that you would expect to occur by chance. What this paper basically argued was, if you reduce latent heat, sorry, if you change land cover, you get a strong and unambiguous reduction in the latent heat flux. These bars are way above the happen by chance, and it doesn't matter which climate model you use. These are different climate models. All of the climate models agree very strongly that if you change the land cover, you deforest large regions, you get a substantial change in latent heat flux, and you don't get a strong impact on the latent heat flux in geographically remote regions. Same with temperature. Rainfall is much noisier. Some models suggest big, strong impact. Some models suggest little impact at all. The moral to this story is, in the areas where you do large-scale deforestation, and this matters into the future if you're doing projections of how the Earth's climate will change in the future, because we will continue to clear or revegetate land, the impact over the regions you do it, in terms of at least the surface energy balance and temperature, is reasonably confidently understood. But that feedback into the atmosphere, how those changes in latent heat and temperature feed into the atmosphere to affect things like rainfall, are much less certain. So, it matters not a great deal how you choose to explore the impact of land cover change on latent or temperature. Doesn't matter which model you use, doesn't matter much about what land surface scheme you use, you're going to get vaguely similar results, broadly similar, they all agree. But if you're using models to explore how land cover change affects rainfall, it's anybody's guess, and it depends, unfortunately, on how you parameterize the boundary layer and convection. Here's another impact of land surface on future climate. It's fire. The red in this diagram is a MODIS, satellite, remotely sensed observation of the scale of fire in the Earth system. And I'm not going to dwell on fire because it's not an area I know very much about, but it is an extremely important driver of some aspects of land surface atmospheric interactions in some regions. You do not get substantial fire where there's not much fuel there. You do see very significant fires over the tropics and parts of the subtropics. Fire makes a profound impact on the land surface and profoundly affects the amount of net radiation subsequently absorbed into that region because it becomes quite dark. It also affects the fluxes consequently because there's no vegetation there immediately after the fire, and therefore there's no transpiration, and that vegetation is not intercepting much rainfall, and the water goes into the soil or runs off over the surface. However, vegetation recovers quite quickly. The nutrients that are released for future vegetation growth is really quite impressive. And as I tried to emphasize in the previous talk, Australian vegetation is just plain weird. This is a eucalypt post-fire, and it's, what's the actual technical term?
Resprouting.
No, it's not resprouting, there's another name for it. Epiphytic leaves?
Yeah.
Epiphytic leaves resprout. This is a eucalypt that's resprouting immediately after fire and is able to begin fixing carbon, intercepting water, transpiring and all that stuff really, really quickly, like a week or two. I remember cycling through Lane Cove National Park like a few weeks after the fires went through there in the 1990s and couldn't understand why the trees were surrounded in ivy. I assumed that ivy had just regrown up over the vegetation, and I thought that was a terrible infestation of weeds, and it turned out to be eucalypts recovering very quickly from fire. But it's truly impressive. If you ever have the chance to walk through post-fire eucalypt forest, it's amazing how fast they recover. One of the things that always perplexes me is people who talk about large-scale fires being a huge source of CO2 into the atmosphere. Because as far as I understand it, if you burn a forest and the forest recovers, it hasn't had much impact on atmospheric CO2. It only matters for atmospheric CO2 on a long time scale if those forests don't regrow. So, for instance, people who've talked in the media about suppressing savanna fires to avoid CO2 emissions, I don't quite understand. Because the savanna burns when it's dry and it regrows next year, and it then burns and regrows and burns and regrows, and I don't see how that's actually having much impact on net carbon emissions. It certainly has an impact on carbon emissions when it's burned, but that carbon is then taken up. So the place that fire makes a big difference to atmospheric CO2 is if you have a large-scale forest and you burn it and it isn't replaced in time by forest, it's replaced by grassland, for example, then that does have a net impact. I'll talk about that a bit later. Other roles of the... I'm moving on now to the role of the land surface on relatively short timescales. And I'm going to talk a little bit about the role of the land in droughts and heat waves. And I'm going to argue, and I'll try and bring it back at the end, to try not to think about these in isolation, because I think they're interwoven with similar processes. So first of all, you'll be aware of something that looks like that. That is the large-scale trend in global temperature. In itself, it doesn't make much of a difference to you or I. It does, however, change the large-scale patterns of the climate. So that trend in temperature leads to some reorganizations in the large-scale patterns of the climate, like potentially changes in the El Niño, La Niña pattern or whatever. And that feeds through multiple other modes of variabilities to get to be really interesting. We really start to see that that trend is superimposed onto those large-scale patterns that in itself feed into the various drivers of climate over Australia, and then filtering through synoptic scale processes like blocking east coast lows, southerly changes and everything else, and feeds on into how the land interacts with the atmosphere. So, the reason we're particularly interested in the role of the land surface on days to seasons is at this end of the sequence where the land is directly influencing the conditions above the land in terms of intensifying processes. But don't think about that in isolation. Think about that as that relates to synoptic scale processes that feed through the modes of variability back to the large scale patterns and up into the global trends. So when I talk to a board, company board, and the people on the board say, we don't care about 4 degrees global warming because 4 degrees is the difference in temperature from Sydney to Armidale, why should we care? The answer is not to be found in that, it's to be found in how that feeds through this hierarchy into a particular region and a particular environment where the land can behave differently with the atmosphere and intensify processes. So I'm particularly interested in this bit of the equation. Those of you working on the large scale, really good work. Those of you connecting that to synoptic systems, really good work. And those of you who are now beginning to think about how those synoptic scale systems can become blocked or cease to be blocked, they're really interesting because the land really only makes a big impact where the atmosphere can be substantially blocked over a region. If it's blocked for a few days in summer, you might get a heat wave. If it's blocked for a few months or longer, you might start to get droughts. So we're interested in how that land surface is intensifying those sorts of synoptic scale processes. And this is how it does it. We have soil moisture down here and time on this axis. And gradually, over time, evaporation depletes the soil moisture. And as it depletes the soil moisture, you change that basic partitioning of available energy from more evaporation rich to more sensible heat rich. That sensible heat mixes up into the boundary layer, gradually deepening the boundary layer and heating the boundary layer. And there's a really good paper by a guy called by a group out of Europe, by Morales, that shows gradually accumulating heat content in the boundary layer being recycled down to the surface on day 2, heating and being cycled back through the boundary layer on day 3, heating and being recycled back into the boundary layer on day 4, gradually intensifying a heat wave. And the difference between a heat wave where you go to the beach and a heat wave where you stay indoors whining about how hot it is outside can be as simple as how many days this process can ripen the boundary layer, generating more and more heat over more and more sequential days. So, let's start with the soil moisture. At the beginning, lots of blue. Blue means water, evaporation, and not much red. Red means sensible, heat, the direct heating of the lower atmosphere. And we move slowly through that time period, slowly increasing the amount of sensible heat relative to the latent heat as the soil dries, such that after a certain number of days, the soil and the land has become desiccated, and that the net radiation that's being absorbed by the surface is being exchanged primarily as sensible heat, not by latent heat. And that then carries on for however long the blocking pattern persists. So if you're working on blocking, and you are able to show to me that under double CO2 the blocking patterns may become more persistent, I'm really interested in that. Because if a blocking pattern can start to last extra 2, 3, 4 days, the consequences on human health of a heat wave that lasts 3 days is trivial compared to a heat wave that lasts 5 or 6 days. An extra day makes a profound difference. So, that intense heating of the boundary layer lasts for however long the blocking pattern lasts. And so the real critical question, the thing that's the key to unlocking the role of the land surface and its evolution over time, is soil moisture. Soil moisture is a pain. This is a figure from Anna, who is sitting over there, and she went and evaluated how well a variety of land surface schemes simulated. This is actually evaporation, but you can think of it as a surrogate for soil moisture in this context. For 6 different places around the planet, these are all different land surface schemes. Only one of them is right, which is of course the one we use, not. And the black is observations. The thick black line is observations on each of these places, and these various lines are the individual land surface schemes simulation of evaporation, which in this case you can use as a surrogate for soil moisture. And we can't show you soil moisture because people don't measure it very often or very well. If you start here, that land surface scheme just there, which is working really well, is very, very, very different to the land surface scheme over here. This one says it's very, very dry very, very soon and stays dry. This one says it slowly gets drier, but it takes much longer for this one to get very dry than this one. This one would be pumping all of its net radiation into the atmosphere as sensible heat, warming the boundary layer, intensifying the heat wave conditions, leading to lots of nasty implications for human health or vegetation surviving. This one wouldn't. And these are 2 different land surface schemes that are run in CMIT5 models. The short story in all of that is we find it very difficult to demonstrate that the land surface schemes are doing the soil moisture very well, which probably translates into them not doing phenomenon related to soil moisture very well. That really matters. This is an image that shows the amplification of maximum annual temperature. TXX is the hottest day of the year. Average temperature is T mean. This is a pattern, if you like, of the amplification of extreme temperatures relative to the mean. And you can see a strong amplification of maximum temperatures over the average over Europe, over North America, and a few other places. This is the change in the evaporative fraction, which is what I've been talking about. It's the latent heat divided by the sum of the latent plus sensible heat. And you can see that these places where we see a strong amplification on maximum temperatures, here, are coincident with a strong change in the evaporative fraction, here and here. All good. We're seeing a strong amplification in the models of extreme temperatures coincident with this change in the partitioning of energy between latent and sensible heat. That's the same picture, slightly differently masked for various reasons, and here are the observations. And if you can see a similarity in how the observed reflects the models, you've got sharp eyes. It's true, over Europe, there's a good, nice correlation between what the models say, which is we're seeing an amplification in the maximum temperatures because of this evaporative fraction, and we see that in the observations. But if you look over North America, which is quite an important place, we see the models showing a strong amplification of temperature by drying, and this change in the evaporative fraction, which is exactly the opposite of what the observations are saying. So, those of you who've been working happily in ocean science, thinking the land surface is easy, could swap over and do land surface science because it's much more challenging. This is also from Anna's work. This is showing the consequences of some of these things. This is the simulated average number of days in the number of frequency of drought. This is for various land surface schemes for 4 different places, 1, 2, 3, 4. The higher the bar, the more frequent the model claims the land surface is in drought. We see the simulated average at 111 days, the observed at 53 days. Short story, the models really struggle to simulate drought well. And if you're currently analysing CMIP5 models for their utility in looking at drought, talk to Anna, because you have a problem because the models are dreadful. We can also do it on magnitude of drought. The models suggest the various CMIP5 models are in drought for 42 days. The observed is 9 days. Models struggle with the magnitude of drought. This all feeds back into soil moisture, and this is all about how well the land surface schemes can deal with the amount of energy they get, the amount of rainfall they get, and partitioning that intelligently to simulate phenomena like this. I suspect most of you think that under double CO2 we see an increase in the frequency of drought. I would challenge you to how confident you would be about that when it's actually apparent that the CMIP5 models do a variable job in simulating drought. So that link between droughts and heat waves is all about the same thing. It's all about soil moisture. Soil moisture is key to how the land surface evolves on timescales of days to seasons. It's really important. It's very hard to measure. Remote sensing techniques only give you soil moisture in the first centimetre or 2 or 3, not the whole of the root zone. We really don't have a good understanding of the observations around soil moisture, and we're pretty sure our land surface schemes are variable in their ability and their utility to accurately simulate the time evolution of soil moisture, which feeds into how reliably our models simulate key phenomena like droughts, and how reliably the land surface contributes to the intensification of key phenomena like heat waves. And that's where the science is, and the new Centre of Excellence is going to resolve these problems. I don't like the giggling. I said, the new Centre of Excellence is going to resolve these problems. On longer time scales, seasons to decades, this is a cool figure, came out of expert analysis of how likely a failure of a key system would be for a given rise in temperature. So when this figure was done, we'd warmed by about 0.8 degrees, I think. This is the committed amount of warming, 2 degrees, 4 degrees, 6 degrees, 8 degrees, nice PDF, and confidently drawn on here at what point an ecosystem collapses. Now, I'd love to ask you all, at what point do you think ENSO would fail as a mode of variability? Because I sure as hell I don't know. I also really don't know at what global average temperature Arctic sea ice would disappear, because it seems to be doing a pretty good job of disappearing at 1 degree. And one of my favourite on here is the Amazon rainforest, which apparently will disappear at warming of 3 degrees. That one. Don't believe it. It's expert analysis. And you lot are now rapidly approaching expert status in your own personal fields, and you have as much legitimacy to put values on here as anybody else. But the consequences of a loss of the Amazon would be quite serious. It holds, and I'm actually quite surprised by how small this number is, 100 billion tons of carbon. Similarly, there's other things that could be triggered as a consequence of climate change as they relate to land surface processes. Soil carbon, for instance, is about 2,500 billion tons. If we manage to melt the permafrost, that's about 1,600 billion tons, all wrapped into current human emissions of about 10 billion tons. In other words, the amount of carbon stored in these systems is jaw-droppingly impressively big. And we don't really want to stuff around with that. We'd kind of like it to be staying there. We do know we can kill ecosystems. This is Kurumba in Queensland. It's, I think, what's that forest called? Mangroves. And it's not absolutely clear why the mangroves have died over hundreds of kilometres. Some people are suggesting it's changes in sea level, some people are suggesting it's some extreme temperatures. I'm not sure I know. But you can see large-scale ecosystem collapse. You can also see large-scale ecosystem collapse in the observations. The top here is in Central Europe, which is being attributed to warming, fewer frosts, and pathogens surviving winter and happily eating into the trees next spring and killing them. On the lower one is drought. It's in California, large-scale ecosystem collapse coincident with no water. Vegetation does not like no water. There's a map from FAO which is basically showing where we're seeing large-scale ecosystem collapse as a consequence of, and the interesting thing is, often different things. Often we see ecosystem collapse being drought. Sometimes it's pests. It depends. But it's quite a global phenomenon. So that collapse of the Amazon rainforest coincident with warming, well, it's not quite as ridiculous as it might sound, because we do see ecosystem collapses occurring associated in various ways to climate change. However, it ain't temperature. This is temperature, right? If you're going to drive a collapse of a large ecosystem on time scales of decades to centuries, it's going to be multiple factors. Temperature, rainfall, changes in net radiation, changes in pests, all triggering changes in competitive advantage of a particular kind of species growing there. And we might see things like transitions from trees to grass or vice versa. I was looking for, I know there's a slide somewhere which shows a hillside from the 1940s and now. And in the 1940s it was scrub and now it's forested as a consequence of the higher CO2 giving the vegetation more of a competitive advantage and being able to grow better. I couldn't find it. There are accelerators to this. So even if climate change is occurring fairly slowly, there are things that nicely accelerate it. This is a borer. It will kill a tree. I once had a really, really nice lime tree, which was a really important tree because it grew limes, which are exquisite in gin and tonics. And a borer, almost like somebody had taken a saw and just cut round the base of the tree about 5 mil deep, cutting off the flow of nutrients to that tree. And it was spectacularly impressive. And it occurred over a weekend. No, over about a week. Bit sad. Fire is another accelerator. If you start to kill off large areas of forest and you suppress the evaporation and you push the sensible heat into the atmosphere, you're drying and warming the landscape, you tend to encourage more fire. And these things, which James Lovelock described in very unpleasant terms once, chainsaws, people who take chainsaws to large forests or deforest large forests in other ways, accelerate things that might be happening more slowly as associated with climate change, and they accelerate them. So, bring some of that back together. The role of land surface in future climate is complex. It's interwoven with CO2, interwoven with energy and water, all interwoven with nutrients, all interwoven with things like fire and land cover change and human activity in a particularly complex interplay of phenomenon which changes the role of the land depending on where you're looking and on what timescales you're looking. So it ain't simple. It's very difficult to write an analysis of the role of the land surface in future climate. It's much easier to choose a phenomenon, heat waves, and think about how the land surface and the evolution of the land surface over time might interact with that heat wave. So if you're working on heat waves, lend an eye to how the land triggers changes in the behavior of heat waves. If you're worrying about drought, ditto. Worry a little bit about the evolution of the land and how that has interplay with drought. And if you're not working on anything that the land surface affects, you're doing well, because land cover change tends to increase runoff and freshwater flow into the ocean. So you can't get away with it even if you're a blue water oceanographer. You have to care about the land surface. The role of the land surface on days to seasons is mainly interplay with soil moisture and changes in the partitioning of the available energy or the net radiation between sensible and latent heat, and with land cover change, and with impacts on things like heat waves and drought. And the role of the land surface on long time scales, I only really talked about its role in terms of ecosystem transitions and abrupt climate change. There are other roles. I could have talked about permafrost. I could have talked about groundwater dynamics. There's plenty of other ways that the land surface can have a long-term driver of climate. It's not dominant over 10 billion tons of carbon emitted a year by humans. It's a set of processes that have interplay with the major drivers in the climate system. And for those of you not working on land surface processes, lend an eye to how the land works and be aware that the land surface is a key component of the system, and talk to the people who are working on land surface processes. And of course, for those of you working on land surface processes, you chose wisely. Thank you.
Questions, Randy?
Or lunch, your choice.
So you mentioned there's if there's a fire that doesn't have any significant vegetation change after, it doesn't make much of it's not a significant carbon sink. Would an example of a fire that could be a potential problem in that case, would that be like the fires in Tasmania or in the Tarkin, where you don't tend to get fires historically, or even the ones in Canada last year? Are they potentially fires that have, resulted in a net carbon increase?
So my understanding of the Canadian fires was there had been large-scale ecosystem dieback, which has been attributed to a variety of factors, one of which is warmer winters and therefore pests surviving winter and attacking the trees earlier in the following season. And so you'd had a large-scale dieback, and then those dead trees burn. If those trees regrow as boreal forest, the CO2 that was released would substantially be taken back up again. The question is, however, whether they will regrow. If you burn a landscape too often, you end up with things like savannas, where there are trees, but you burn too often for a forest to regenerate. And a savanna, I would imagine, has less carbon in it than a fully grown, dense subtropical forest. So it does depend on what a burned landscape recovers to. In things like Lane Cove National Park, or the Royal National Park, which was substantially burned, I don't know if anyone has actually measured the carbon per square metre in those forests, but my suspicion is it's fairly similar to what it was before it burned. It's recovering, in other words. Whereas my understanding of the Tasmanian fires is they were in areas which shouldn't have burned and would take a hell of a long time to recover. And there's a pretty good chance, I would think, of other fires coming through that landscape to prohibit a full-scale recovery. That's my guess.
I can address your question a bit as well. Fires in Australia that have had a long-term impact on vegetation. The best example that I found in my research is the 2003 and 2007 fires in the alpine regions in Victoria and New South Wales. The bush has never recovered, it's been 10, 15 years and it hasn't come back.
But that's not a lot. So
Yeah.
in human timescales, 15, 20, 30 years is a long time, right? But in terms of a landscape like parts of the Snowy Mountains, those are ancient landscapes, and the vegetation that you see there, a lot of it's residual from height of the last ice age. So it could take thousands of years to recover if it's given the chance. It just depends on the landscape. Eucalypts grow pretty fast, so that's one advantage, but they don't grow pretty fast in the alpine region.
Has anyone tried to estimate what proportion of Australia-wide temperature warming over the last 100 years might be due to land use change?
They have. There was a brilliant paper by, Gemma Narisma. The second author was me, which is why I was being sarcastic about how brilliant it was, that did that some years ago, but it was done with very primitive modelling, or relatively primitive modelling, and it was focusing on relatively short timescales. Gemma was able to show that a sizable fraction of the warming then observed could be due to large-scale deforestation, which has been experienced over Australia. I think I would like to emphasise from that work could have been due to, not was due to. Clearly, some of the trends in temperature aren't due to land cover change. Another very interesting question, though, is if you have large-scale forests and you impose warming on the forest, the amount of that warming is expressed quite differently depending on whether it's forests or grasses or crops or urban landscapes. So another really interesting question is if you do have a warming forcing on Australia, how that's expressed spatially depends upon, in part, the nature of the land surface. But no, some of the warming signal over Australia is almost certainly due to the large-scale land clearance. But for the card-carrying climate skeptics in the room, it's hard to explain the patterns of warming as related to land cover change in the middle of the Pacific. And some people have attempted to do that. It's quite hard because there's no vegetation there to clear. I always think of the land as a moderating or amplifying process on the large scale, not as in itself a driver. But once you get down to small enough scales, for instance a city, that city can have its own microclimate, quite distinct from the larger scale regional climate, and we don't tend to take that into account in our projections. Lunch calls.
Thanks, Andrew.